In this video, we'll talk about the basic idea of errors in physics. In other subjects, for example, in philosophy or TOK, the subjects that you take in IB, that would introduce you the concepts of logical fallacy. So that is kind of an error as well. In statistics, if you have learned about it, there are two kinds of error. That's called the type 1 error and type 2 error, depending on the error that is having the truth to be positive but the test to be negative, or the other way around. If you try to put it in the context of COVID-19, so that would be those cases that we heard in the news where maybe a certain person actually having COVID-19 but the tests were diagnosed to be negative, or the other way around, that the person actually doesn't have COVID-19 but the test turned out to be positive. So those two will also be an error in statistics. And so if you think about the fundamental idea of errors in or around all the subjects, all the different kind of discipline, it is basically referring to how your perception are different from the actual truth. There are two kinds of error categories in physics when we do experiments. One is called systematic error. Another kind is called the random error. And there are two adjectives that is associated with it. One is precise, that is linked to random error. So when you say something that is precise, that means the random error is small, or the other way around, when it is not precise, then random error is large. Similarly, for accurate, that will be linked to the systematic error. So saying if it is accurate, that means the systematic error is small. So down below here, I would like you to think about which one is accurate, which one is, you can talk about whether it's accurate or precise or both for each picture. So pause the video, try it out yourself, and I'll explain to you one by one.
A few moments later.
Alright, let's do the easiest one first. I'm pretty sure that everyone will get it right. That is for the top left one, it will be accurate and precise because it is just so good, because you can see all four of the attempt were all gone into the middle. So assuming, of course, middle is what we want to find. The worst ones, however, is also very easy because obviously it is not accurate and not precise. Alright, and for the other two, then you have to again think about how that was linked to random error and systematic error, and I think you can kind of guess the idea of it. So for the one on the top right, if you try to think about the average of these, it's around actually still in the middle if you take the average. So it is still accurate because in terms of the error, you don't have a very systematic way of having the error offset to certain direction, so it's accurate. But then you can see it is kind of random because it go over many different places, some on the top, some on the left, some on the right, so it is not precise. And so lastly, for the one at the bottom left is now very obvious, so it must be off from the center. You can see these cluster of data are offset from the center, so it is not accurate comparing, of course, to the others. And however, it is very precise. Precise actually means, again, having a very small random error. So that means every time it's almost the same. So you are consistently miss from the center and going to the very tiny area that you cover. In order to get you to understand the idea of accurate and precise and also the two errors easily, I want to use numbers to visualize it. So let's imagine we are trying to do an experiment to find out the gravitational acceleration g of the Earth. So everyone knows it's 9.81 in our literature, but let's say it's 9.8, actually 0.6. Let's take one more significant here to be so-called the truth value. So let's say there are 4 students here who are supposed to be in these 4 different kind of cases, then let me show you maybe the 2 of them, and you can work out the other 2 and see whether you understand. So let me do the easiest one, of course. The one that are accurate and precise would probably have the experiment result to find out to be G equals to 9.804, let's say, so very close to the so-called true value, plus or minus 0.001. Okay, so first of all, let me explain. So the idea why it is accurate is because this value, the average value, is very close to the so-called true value or the accepted value, right? Very close already. As for the idea of precision, why it is precise is because the uncertainty, the plus or minus thing, is called the absolute uncertainty. That is very small, right? If you think about it, like 0.001 is very small. You have a lot of decimal place. So that is an idea of precise. Similarly, if you think of a case where it is not accurate and not precise, so that particular student, of course, is very horrible, then maybe he or she result, we have find the result that is, let's say 16, how about that, plus or minus 1. Okay, so if you look at that, then yeah, obviously 16 is way bigger or way off from our accepted value 9.81 or even 10. And also if you look at the absolute uncertainty, it is plus or minus 1 here, which is relative much larger than the one we talked about just now, 0.001. So it's basically 1,000 times larger. So that's why it is not precise as well. So for now, can I ask you to work out the visualizations with the numbers in the other 2 cases? Pause the video, try it now, and I'll give you my examples.
A few moments later.
Alright, I hope it's easy for you. So let me show you my choice of example. So you can be different from mine, of course, but then you should get the main idea. So for this example, it is accurate, so it should be close to the truth number or the accepted number, but not very precise. So probably I will go for 10 plus or minus 1 in this case. Notice that your uncertainty, absolute uncertainty, has to match the same decimal place. I'm not sure if you realize that. So if you are 0.001, then your final answer, average number, has to be in the same decimal place as well. Same here. If this is the digit you are doing, then it will be the same digit for your average values. So you can't say it is 10 plus or minus 0.2, right? You can't do that. We'll explain more later on. So let's just keep it as 1 first. So for not accurate but precise, okay, that will be quite interesting. I will use an example of maybe say even worse. So say let's say 22.345 plus or minus 0.001. Okay, so it's ridiculously far away from 9.1, but then somehow every time you do is located on the same spot. So the uncertainty, absolute uncertainty, is very small, and so that probably might be something wrong with your systematic error for sure. Oh, I forgot one thing that is very important. I should give all of these a unit. Okay, so you may want to add it just to be more precise. So all of them, you have to put a bracket that is meter per second square for each of them. If you don't like to express this way, you may also express it like, let's say this one. You can express it like with the unit separately. So 9.804 meter per second square plus or minus 0.001 meter per second square. You can do it this way, but obviously you have to write more, so I like bracket. Some of you may say, hey, can I do this then? Right? You cannot, because one thing is you may have different units for each of them. So we, as physicists, we don't take assumption like this. I mean, if you write it like this, then we'll just know that you forgot to put down unit, because one may put this as a km per hour square. You can actually do that. I mean, you can have a one unit like this and the other unit could be different. It's actually possible. Of course, I would always encourage you to be consistent across the average value and also the absolute uncertainties value. So I'll say it would just to be the best to keep a bracket and then plus or minus thing like all the things inside with the unit outside here. So let's just keep this as the convention for us. These 4 diagrams is only for illustrating the abstract ideas only. You probably would not be doing an experiment that is flowing the dots. So what if it is in an actual experiment then with the actual data then? So let me give you some more context so hopefully you can understand more. So here is an example. If you're doing an experiment on, again, finding out the gravitational acceleration, and you have done 1, 2, 3, 4, 5, 6 trials, and how would you like to express your measurement here? Okay, so there's no change between each trial, so somehow for some reason it just measure to be different at the end. So you would need to express the value of G here with a number which is we call the average number, average values, and a number at the back called the absolute uncertainty. So pause the video now, think about how you would like to express it, and I will show you how I will do it later.
A few moments later. A few inches later. 2 hours later. 1 eternity later.
There are 2 ways of doing it which are both acceptable in IB physics. So one way that you may find from the textbook as well is for the average number is really just taking the average. So what you do is add them up all together. So 8.9 plus 7.8 plus 9.6 plus 8.8 plus 7.9 plus 10.2 divide by 6. Then you find the value of 8.86667, right, for more digit. But then once again, if you recall what you learned in the previous a few previous videos, then you know you can't take as many significant figures, so you can probably take only 2 in this case. So we'll keep it as 8.9 then, or according to the rule of thumb that we learned. And as for the uncertainty, one way of doing it is people may use something called standard deviation. However, I would not agree, or I would not encourage you to use standard deviation at all, because obviously in the exam setting you probably would not be able to find standard deviation quickly. I know in the calculator you can do that, but it's not required in physics. And the other thing is more about a fundamental idea of that statistic. So what we do for standard deviation is, if you have a bell curve, if you have heard about normal distribution in maths, then yes, then you can try to use the bell curve to standardize it, to model it, and standard deviation is a way to measure how the number were distributed. But then here it's not really applicable, because first of all, our measurement may not be following a normal distribution. Secondly, when you want to use standard deviation, actually your sample size cannot be just like 6. It won't be meaningful from certain statistics sense. So I don't want to go too deep there, but normally if you use standard deviation, you may probably need to have like 20 or 30 samples before you try to calculate the sample standard deviation. Just like maybe your exam score, the teachers may calculate the standard deviation. That will be useful, but for 6 trial, the number itself is not going to be very meaningful or reliable. So how do we actually do it then, you may ask? So the way that we all agree in IB physics is we will use something called the half range method. Okay, so that is finding out, in terms of equation, I can write down here. So that is maximum minus minimum divided by 2. Okay, so that is to say, it will be the maximum, which is 10.2, minus the minimum, which is 7.8 here, and then you'll be able to find the uncertainty. So in this case, at the end you'll find out 8.9 plus or minus 1.2. Alright, exact number 1.2, so I guess we just take 1.2. So that will be your final answer. Another approach, which I probably would prefer more, is for the average value, instead of really taking the average like what you do in mathematics, like the mean value, of course. In physics, I prefer something similar to the half-range method. So just now it was maximum minus minimum divided by 2 for the actual uncertainty, but here I could actually do maximum plus minimum divided by 2. So you also find the half range value of it. So in our case here, then again it will be 10.2 plus 7.8 divided by 2. So this is the average value. For the uncertainty, we'll still be using the half-range method, so it will still be 1.2. And so in this case, your average value would probably be different, and that will be 9 using my calculator. So again, because of what you should have learned about sig fig and decimal place, this one should express as 9.0 instead. Okay, so I deliberately set you up with these examples, so hopefully can show you the two different approaches and which one is more logically reasonable. So for me, I do think this one is better. Do you know why? I give you maybe 5 seconds to think about it. Alright, I forgot to put down the units again, so now I just add it up. Back to our question. If you look at the approach I suggest, and if you try to find out the worst case, then you will be able to work out the range. So what it means is, what is the worst case? So 9.0 minus 1.2 will be 7.8. That will be the minimum you can get with this expression. For the maximum, or I can maybe use a more mathematical way to express, so that will be this. Okay, if okay, G maybe, not X. Alright, for the maximum, it will be 10.2. Okay, so this is what it is for the approach that I will agree. For the one that is mentioned by the textbook, or just simply intuitively thinking by taking the average mean, then the range that it covers would then be slightly off. That would be 7.7 to 10.1. Okay, so think about why this is better is because if you look at the original data, this is the minimum, this is the maximum, and all the other data are falling within this range. So if you ask me, then I would say the approach on the right is a approach that really reflects all these 6 trials, all the data that you got fully, while for the one on the left, it's a good estimation, but then it doesn't reflect fully. So I'll prefer the one that is on the right, which means again you have to use max plus mean divided by 2 for the average value. The last question here is about the electronic balance. However, this idea can be put to other general apparatus as well. Usually that is involve more digits, so more precise instrument, usually maybe the digital one. So example could be other than electronic balance, could be say the vernier equipment, that may be the Newton meter, or it can be a magnetic field strength sensor as well. So the main issue that I would want to carry out here is there might be fluctuation in your reading. So that is to say, for example, if you have an electronic balance, you may have experience that you want to measure something. All right. In most of the time, when you say when people are doing cooking, you don't have that because the balance that you are using is probably up to 1 gram only. Okay, so in that case, probably no way that it will fluctuate. I mean, if it is 10 gram, it's just 10 gram, right? It won't suddenly jump to 9 gram or 8 gram or 11 grams. But then if you got more digit, then the atmosphere, because they have air pressure and maybe the wind as well, may give you a fluctuation in terms of the reading. So I don't know whether you have experience in chemistry as well, but then let's say in this case, our reading range from 16.42 to 16.26. So maybe there are times where you may get numbers in between it, so maybe 16.33, etc. But then for a certain fixed period, for example, maybe within the 10 seconds, so your eyes is just staring at it, or you can use a video to record it, you'll find out the maximum and minimum that you can observe will be these two numbers. Okay, so what you can do to express the final value for this trial then. So I will give you some time, pause the video, think about what you learned in the previous question and how you express it here.
A few moments later.
Alright, so according to the approach that I prefer, obviously the number that is for the average will be the maximum minus the minimum, plus minimum divided by 2, and for the uncertainty would be the minus. Alright, so that would be 16.42 plus 16.26 divided by 2 plus or minus the same thing but minus. So using your calculator, you can find out, or you can actually probably tell directly. That will be 16.34 plus or minus 0.08. Okay, so that could be the final answer, because you can see, like I said, this digit match with this digit, and I think that's all good. And here we got 2 decimal places, and this is 2, yeah, we are all good with this. So this should be the final answer.